Hello and welcome to another video. In this video, I'm going to talk about big O notation in computer science. So before I start, let me give you an example and see what exactly is the idea behind big O notation. I won't waste much time. Yeah. So let's say we have a computer A and we have computer B. Computer is much faster than computer B, and we are running uh, another algorithm on computer A and another algorithm on computer B. So like we are running two different algorithms on computer A and computer B. Now what happens, uh, you know here we are trying to solve a particular problem and we are implementing two different algorithms on computer A and computer B. Computer is much faster as compared to computer B, which is a very slow machine, you can say. Now when we are trying to increase the size of the input, here we have 16, so the computer A is taking just 8 nanoseconds, computer B is taking 100,000. When we have input size of 63, computer A is just taking 32 nanoseconds and computer B is taking 150k. Now whenever we are increasing the size of this input, computer A until here is performing little bit much better as compared to computer B. Now if you are just trying to test your program just by limiting your input to some number, then you will realize that computer A is way better than computer B, because computer B is taking this much 250 k nanoseconds. So like it's a really slow. But if you continue to run the program for higher input sizes, so here let's say we have input size of 1 million, then both the computers are doing the calculation in the same time. But if you increase the input size to 4 million, computer A is taking 2 million nanoseconds, the computer B is just taking 550k. So here as we can see that the time growth, the amount of time that computer B is taking, it's not growing that much as compared to the time computer A is taking. So here as you can see, the computer A is taking, like here it is taking 8 million nanoseconds. So it's huge for this 16 million input. So this is the difference. So if you are trying to test your algorithm, and if you are not testing it for majority of the inputs, then you will not realize how efficient your programming. I'll come to that. Now let's see what happens when we increase the input size to this 63,070 10 to 10 to power 12. So computer A will take 1 year, computer B will take just 1.375 milliseconds. So as you can see that despite being a powerful computer, computer A is not able to solve this particular problem using its algorithm within a really efficient time. So you want your algorithm to be solvable within a specific time. So you do not want to run your algorithm for like year or 2 years, so that's not really feasible. And computer B is just taking 1.375 milliseconds, although both are running two different algorithms obviously, but they're solving same problem. So as you can see, computer B is far more efficient in the long run as compared to computer A. Okay, long run as in for the input size that's big. Okay, now the idea of big O notation is to find an algorithm that is efficient especially for bigger input size. So this is the idea behind big O notation. Okay, actually it is a concept taken from mathematics, but we use it in computer science to actually analyze our algorithms to see how efficient our algorithm is in terms of scalability. Whenever we are trying to increase the input size, how efficient it will be in the long run. So you do not want like 1 year, 2 year, 3 years time, right? You want to solve your program within milliseconds. So like you want to be efficient. Now let me tell you why big O was introduced. So let's say I have a computer which has like 4 GB RAM, and you have a computer which has like GPU and CPUs which have like 16 GB RAM or like 32 GB RAM, something like that. Now, one way of measuring our efficiency of algorithm is we can simply take the time difference. Like we can calculate the time before running the algorithm and time after running the algorithm, and we can subtract that to find how much time our uh, program is taking to run, and we can simply say that this is the time. But that is not going to happen on my computer, because I have like just 4 GB RAM, and maybe my CPU capacity is not that much, so the performance of like uh, program on my computer and on your computer will differ, because you have, let's say, a more powerful CPU, so the performance will vary on different computers. So the time difference will not be a really great approach to measure the efficiency of an algorithm. So um, we can uh, we can discard that. Now, another way to do analysis of algorithm is to test it on multiple input sizes, but it is not going to take into account all the input sizes that you have not tested, so that is also not a good idea. So that means here, if you have tested your program only till 1000 input sizes, then you'll just say that, yeah, computer A is sorry, the algorithm on computer A is like better than computer B. But you have not tested for these input sizes, so you won't be able to figure out which algorithm was better. So we cannot simply make a conclusion that our algorithm is efficient just by testing a few input sizes. So that is not really a good approach, and that is not also going to give you a really efficient algorithm, because in the long run, or let's say if you are deploying your algorithm in in your real world application, then you do not want your program to keep running forever. So that is something you have to keep in mind. So we have to develop a way to analyze our algorithm, especially for worst case scenario, because we do not know what input a user is going to enter. So we have to prepare our algorithm for worst case scenario, so that we can analyze it for its efficiency. So all the cases within the worst case are already like taken into account if we are going to test it for worst case scenario. So we have to figure out a way. So a person named David Knuth introduced this idea of asymptotic notations in computer science. He has taken this idea from number theory, and he introduced this idea in computer science to analyze the efficiency of algorithms. So there are various types of asymptotic notations. I'll come to the part of these algorithms, but let's first talk about the mathematics of asymptotic notations. Okay, uh, the these definitions may look a little bit scary, but don't be scared, because the secret of this understanding of big O notation lies in understanding these definitions, because this is what uh, you know what is this concept is what we use in analyzing our algorithms. If you know the definition, you will be able to easily figure out the efficiency of your algorithms, so it's not a big deal. So let's first talk about the mathematics, and we'll talk about the algorithm part later on. Okay, so the big O notation, this is the most popular one, but there are other notations as well. So there is little o, then we have big omega, then we have little omega, and there is big theta. So these are not very different to each other, but let me tell you what exactly is the difference. So let's first talk about big O notations. So in big O notation, this is the definition, mathematical definition. This is not about the algorithm, this is just the mathematical definition. So what it says that if we have a function fn and we have another function gn. Okay, so let fn and gn be a function that map positive integers to positive real numbers. So let's forget this part. Okay, let's forget this part, so that we do not want to get confused with this whole definition. So let's say we have two functions, fn and gn, and we say that fn is ogn. It is simply a way of saying that fn is ogn, or fn belongs to ogn, if there exists a real constant c greater than 0, and there exists an integer constant n naught greater than equal to 1 such that fn is less than c into gn for every integer n greater than n naught. This means for sufficiently large n, the function fn will not grow faster than a constant multiple of gn. So what this means? This simply means, we have two functions fn and gn, and we have a c, constant c, which is greater than 0, so it is positive only, and we have this n naught greater than equal to 1. So this is nothing but a threshold. So a threshold that we are taking into account, which is greater than and equal to 1. So what happens, we after this threshold, whenever we are trying to enter the value of n in function, what will happen, it will always be less than equal to c into gn. So this is something that always happens if n is greater than n naught. That means the function fn will always be like, it will be below this gn, or equal to gn whenever you are trying to, like, plot the graph. So let me show you the graph and then it will become much clear. So here we have a function fn, then we have gn, which is nothing but the first bigger term from this function, and then we have cgn. So c is something that we have taken on our own, so you have to figure out c on your own. So there is no particular rule, you can simply take any c. Usually we try to take the one coefficient bigger than this one, so that is something you have to figure out. And then we have n naught. So n naught is nothing but a threshold that we take. Now what happens after this threshold, whenever we try to enter a value of n, this particular function fn will always be below this. So always below means below, less than equal to that c into gn. So let's say this blue line, graphically it becomes a little easier to understand. So this blue one here is fn. Now this gn is this thing, right? This gn is, let's say, this function. Now what the definition says, the big O notation says, the c into gn, the c into gn will always be greater than equal to fn, or fn will always be less than equal to cgn. So this is cgn and fn is here only. So this means this is not going to cross this particular graph. So it is always going to be around this particular region, within this region. So this region, it is not going to cross this particular curve. So it is not going to go out of this particular range. So it is always going to be within this range, and this is what we call big O notation. Now what exactly it means? So what this means is our function is going to always be within certain range no matter the input size. This means if we can figure out the outer range, so the maximum range, the worst case scenario, then we'll be able to say that our algorithm won't perform worse than this thing. So this means we can take the upper limit and we can simply say that yes, this algorithm has this level of efficiency. So this is the concept we use in computer science. So what we say, we simply say that no matter the input size, our algorithm will not go beyond this particular limit. So this is the simple idea that we use in computer science. Now, little o notation, we simply remove the equal to sign, and we say that it is nothing but fn less than equal to cgn. In big O notation, big omega notation, sorry, we have fn greater than equal to cgn. That means fn will always stay above that, always stay above and equal to this cgn. In little omega, we have fn always greater than cgn. Now big theta is nothing but it is combination of fn and big O notation, big theta is nothing but it is combination of big O and big omega. So this is just it's like it belongs to both the cases. So this is the difference here. Now in practice, our goal is to figure out the most efficient algorithm for our problem. So we create a function which is nothing but a function of the input size, and we try to figure out what is the maximum, in the worst case, how it will perform. So we try to find the big O of that particular, function. So uh, what happens when we say big O of 1? This means we are just performing a particular operation, like within a particular amount of time. So that means we are taking the same amount of time to execute certain thing. So no matter the input size, the execution will take the same amount of time, because time, correlates with this execution. We call it time complexity. That is the reason why we call time complexities in programming. But it's actually like a way of saying that yes, this will not take more than this much. Okay, so it's like, when you are saying it is O of 1, and it will not take more than this. So that's what it means. So here, as you can see, it is a constant time. This means an algorithm that always takes the same amount of time or space to execute regardless of the size of the input. For example, accessing an element in an array by indexing or performing basic arithmetic operation. This means if you're taking any element in an array, then it will take the same amount of time no matter what is the input size. Even if you increase in the input size, it will take the same amount of time. But if you have to iterate over the elements within that particular list or array, then uh, the amount of time it will take to execute that program will grow linearly, because you have to go through each element. So if you're increasing this number of elements, then the time that is going to be needed will increase as well. So it will have a linear time. That means it will have big O of n. That means it is not going to go beyond this. Similarly, you have logarithmic time, then you have quadratic time, exponential time, factorial time, and polynomial time. In practice, you may have some other functions. So this is not some kind of like a rule that you are going to get something between something like this. You may get another function. So it is simply a function. So the gn, this is basically gn. So you can get anything. And if you want to compare that which algorithm is like more efficient, you simply have to figure out the most dominant term. Okay, try to analyze each operation, each basic operation in your program. I'll discuss about this, but just listen to me carefully here. Try to analyze each basic operation in your program and see how much, how many operations you are doing. So if you have to iterate, you will be doing it n times. If you have to do it like, no matter the input size, if you are doing it just once, then it will be just big O of n, or 1, sorry. Then you can simply, add them and figure out which is the bigger term, the dominating term. Then you have to just select the dominating term, and that will be your big O(n), big O notation. So like that will be your time complexity. You can even plot the graph and figure out which two algorithms are, more efficient. So whichever graph stays below, then you can simply select that particular algorithm. But most commonly you will come across these uh, these time complexities: constant time, linear time, logarithmic time, quadratic time, exponential time, factorial time, polynomial time. So let's plot them and see what happens. Okay, I'll come back to the explanation which I did about how to figure out the time complexity, but let's first see the graphs here. So here we have constant, linear, logarithmic, n log. Okay, now as you can see that n log is growing faster. Okay, as the input size increases, n log is growing, but the linear but the constant and logarithmics are just staying, they are not growing too much, but the linear is growing with the linear rate. So as you can see, if you have to choose here, you will be going with constant first. Constant is more efficient. Then you have this logarithmic, and then you have linear, and then you have n log. Okay, now if you have quadratic, big O, then what you can see here, quadratic and exponential and cubic. Then as you can see here, this is quadratic, then you have this as cubic, and then you have this exponential. So as you can see, initially the exponential function, exponential like big O of that particular thing, so initially it was performing better as compared to the cubic one. But after certain input size, the performance of exponential, like it degraded. So like it exploded here. So as the input size increased, the algorithm which was big O of this exponential, it was not very efficient after a certain point. So if you have to choose, then we'll be going with the cubic one. If you have three options, then you would be going with quadratic. Similarly, if you want to plot all of the graphs, then you will realize that this is the whole picture. So you can simply plot the graph and analyze that which algorithm is more efficient, but you can do that only after figuring out which is the most dominant term in your algorithm analysis. I'll come to that point and then I'll discuss this. Now let's see what is happening here. So as you can see, uh, the conclusion here is just because an algorithm is doing better for small input size, that does not mean it's going to do better for bigger input size. So that's where this big O notation shines. Now let's see how we can analyze our algorithms for this, figuring out that what is the maximum limit. Okay, what is the growth rate that we can expect our algorithm to achieve. So here let's say we have an example here, n equal to length array. So this is nothing but we are here we are just doing it once. So that is something I have not written here, but yeah. Now here we have for loop. So for loop, again we are doing it n times, so we'll simply write on. Okay, and this accessing an array of this accessing an element of this particular array, that is just happening in big O1, because no matter the input length, it will always take that much a constant time, but this one will grow linearly. So this is nothing but a the growth factor. So like what we are saying here, if we are going to perform this operation, then the growth will happen with this rate. If you're going to perform this operation, the growth will happen at this rate. Okay, here I have not written anything, but yeah, that will also O1. So yeah, now again we have this for loop, and within that for loop we have another for loop. So here the growth rate of this particular block, okay, so this will be on, because we are going through each element. Okay, so as the element increases, there will be linear growth. Again here we have a nested loop. So here again we'll be going through each element. So again it will have on. Now here we are trying to access the elements and we are summing them. So this is nothing but again O1. So this is no matter the size, we are going to get that constant performance, linear growth only, constant growth only. Now what we can see about this particular block, that this particular block is big O of n square, because we have two n's, right? So we are going once, and then again within that particular loop we are going again for each element. So we can say that this is a big O of n square. So that means it is not going to grow more than n square. Now for this we have same explanation. Again we have three loops, on, and here we have on. So it is simply on to power 3. So this means it is not going to go beyond that on raised to power 3. So what we can do in order to figure out this whole function, like how efficient this function is, we can simply write them in an equation fashion, like O1 plus On plus 1, again this On square, then On cube. So once you have written it in that fashion, what we can do, we can simply select the most dominating term. So most dominating term here will be on raised to power 3. Why? Because on square will not grow much in the long run, because we are considering the worst case, remember. Then in the long run, the only term that will dominate in this particular function will be on raised to power 3. So we are going to only focus on that particular term. So the overall time complexity of this particular code will be on raised to power 3. So that is that is the way to analyze the time complexity of your code. So you can do that based on your program, like it comes with practice, to be honest. But the thing you have to keep in mind, that you have to focus on the basic operations that are happening, and you have to just see how many times you're performing that particular operation, and what growth rate you would be expecting. So if it is a for loop, then you would have to go through each element, and you have to also keep in mind the length of that particular list or whatever thing you are working with. So you have to keep that in mind, that if I'm going to increase the input size, will I have to perform some extra calculations. So that is also important. So you have to think in terms of rate of growth, not in terms of number of basic operations. But yeah, basic operations matters, but still you have to think in terms of the growth rate. Like if you are going to add more elements, then will you be performing more operations. So that's how you can think about this. Now you can express them as a function. So like you can add them together, and you can just select the most dominant term. So this most dominant term, o raised to power 3, is nothing but gn. So if you multiply it with some constant, then this entire function won't grow more than that. Okay, but in practice we simply select this the most dominating term, and we simply like select that. We ignore that constant term, because a small constant term won't matter. But obviously you have to keep in mind that your constant term cannot be too big, as in like it cannot be 100 raised to power billion. So that is something you have to keep in mind, that in practice we simply ignore the constant term. That means c into gn. We simply compare with the gn, and we just approximate that this is the maximum, like our function can go. This is the this is the worst it can get. So that is how you can analyze. So here in our example of yeah, in this example we simply selected gn as n raised to power 2, and we were taking c equal to 4. Okay, but in practice we ignore this particular part c, and we only compare to this, and we just say that it is not going to go more than this, right? So that's something you have to keep in mind. With practice you'll be able to get the idea, like how exactly you can perform this whole thing. But overall, big O notation is a way to figure out how your program will perform if you increase the number of input. So it is basically a way of figuring out, like how you can compare two algorithms together, and you can simply find the ON of one algorithm. So let's say if you have written this function, here we figure out that O raised to power 3, then you can simply plot a graph. If you have another function, you can simply find the time complexity of that particular graph, and you can plot them together, and you can see which graph is less than the one another one. And based on your analysis you can come to a conclusion that yes, this one is more efficient as compared to the another one. So that's how you can do that. In future videos I'll be uploading more videos on the related topics, and in those videos I'll be discussing more about this data structures and algorithms. So please make sure to subscribe to this channel, and if you have any questions, do let me know. I have also shared this particular notebook. You can find the link in the description. It's available on my GitHub. So yeah, thanks for watching this video. Have a nice day.